Okay, welcome back, PlayBASIC coders. Let's take another quick look at our little low-res engine. What have we added to it lately? So we've got sprites, raster bars were added to it, and what I added just before was actually depth sorting to sprites. So you can actually control the depth. These characters here, these rectangles, they're sprites, and this is their depth within the scene. So we'll do, I'm controlling sprite 100 and it's at a depth of 0. So if I use I've just hooked it to the mouse scroll wheel, push it up, nothing's really happening. It's at 104 now depth, so we're still behind these guys because they're in front, they're 120. If I go forward a bit further, up to 100, now we're second priority, we're in front of sprite 1 but behind the other one, so we just push forward again, keep going, appearing in front of them. The way it works is it uses the depth and the sprite index when doing the scene sort, so it's kind of a quick cheat to give us something that resembles depth sorting. That does mean that because we're using the index as part of the depth of the sprite, that a sprite that was at a depth of 100, say, and that if we have sprite of index 1 and a depth of 100, and a sprite that's at 100 as well but has a higher index, then the one with the higher index will be rendered after the lower one. I'll show you the code anyway. I've got added a bit of a secondary thing here to stretch the window. The screen here is 256 by 256. It's 2 by 2. I think we've got all the basic things showing. We've got a bunch of text displaying and things. We've lost a bit of frame rate because we're capturing, but the raster bars are in the background. They're just attached to whatever colour we want to attach them to. Might add a few extra little features to that so you can mess around with, play with something different, do something different for once. Let's check the code out that does the depth sorting. So if we go to the library itself, the low-res library, at the moment it's rendering the depths in here. Of course you wouldn't do that. You don't really need to. So we're drawing the ordered sprites. We're running through, we've got a limited number of them, so just set it up here using the constant that's declared at the top of the library. So you can't use sprite 0, we don't even bother checking it. You could technically create sprite 0, but I thought it was kind of silly having a sprite 0 in case you wanted to make your own, create free sprite, new sprite, whatever you wanted to call it. So what this does is it just runs through the sprites, gets a pointer to the sprite table, multiplies the current index by the size of the sprite, because they're literally a chunk of memory. This includes a header and the pixel data. We'll have a look at that in a second. I think the sprites are limited to a size of 32 by 32 bytes, that is, plus the header. So the header's got like a status, a width, a height, a handle, so you can displace the sprite from its current position if you wanted to. I think it's about all we really need to store. So the width and height, those things there. So in this routine anyway, we're computing a pointer to this current sprite, checking its status. If it hasn't been created, we just avoid this sprite. We don't need to depth sort it or render it. If it exists, we go, okay, where are you on screen? If it's off screen, we just go, don't bother with the sprite. We won't bother sorting it or rendering it at all. We do the same thing for the y-axis. The one this is doing for the x-axis, by the way. Same for the y-axis. So if we've got to here, then we are on screen, at least either completely or partially. We probably could have a flag there saying, giving a hint to the renderer as to how to render this later, but I haven't bothered. So we take the sprite's current depth. The depth has a limit of 2 to the 16. So we're shifting the depth across, and then we're adding the index to it. So we can then, into this array that we're going to use for sorting, because what we want to do is we want to sort these values and then pull the two values apart to get the index of the sprite to draw again later. So it just saves having to have two parallel arrays or store the data in somewhere else, or write a custom sort routine. Couldn't be bothered. So this loop here is processing what sprites we need to sort into our little sort array. At the end of this, we end up with, if there's anything that we need to actually sort, we pass it into here. Just use the internal sort array. That Y position is just for display purposes actually. We just sort from the bottom result to the top, and it would, I think by default it uses a quick sort. Anyway, once they're sorted, we run through the sorted items, which has the Z values pushed up into the top 16 bits of the 32-bit value, and the index is in the bottom 16 bits. So to get the index, we just grab this depth value and mask off the bits we want. So it's the bottom 16 bits. So the actual Z value is removed and we're left with the index. That's why we have the behavior where if we have two sprites that are the same depth, but one has a higher index than the other, they'll be sorted in that particular order. It's just a byproduct of the implementation here. Fair enough. Anyway, so we've got a sprite index. We get a pointer to this to get its location on screen. Actually, that's only really for the display purposes there. It's not really for anything else. Grabbing the sprite index. No, we don't need that at all. Sorry, just sprite depth, yeah, and that there. So all of this, once we've got the index, we can just call draw sprite, which has a bit of repetition really. It's just doing the same safety check. Checks if the index is legal. Have a look at that code there. We're going, give me a sprite pointer, using our index to compute a pointer to the sprite. If it returns 0, the sprite doesn't exist, so get out of there. It should never return this. I better leave that there for safety reasons or legacy reasons without going to check the sprite pointer. So the sprite drawing algorithm is literally just a rectangle copy. We're running across the row, reading the source pixel, checking if it's 0. If it's 0, it gets screened out. So we treat a byte 0 as being a transparent pixel. Everything else is actually going to be output to the buffer. But I mean, as you can see, when we're calling this function from the sorted routine, some of this stuff has already been done. I mean, you probably could just make a secondary version of this draw sprite that has, we pass in a pointer to it, and maybe it just does the work from down below that or something like that. Not too concerned about it. It's just it's a fun little project. It's a side project and already. But anyway, so once we've gone through and computed the Zs and the indexes, sorted these things in order, our drawing is really just this. That's all we need to draw it. The stuff there is only really just about having the text displayed on screen. Kind of fun doing these little side projects. You tend to reimagine how you would do PB's own sprite commands again. I think what I'll just do is I'll package this and just put it up in the thread, and I think we need some probably a copy function to copy a sprite in or out. Just take a look at that sprite structure there. If we go back to it, where are we? This is our sprite. It's one type structure, so we have a status as an integer, a depth, which is the Z depth, screen coordinates, our handle, our width and height, and we have a pixel buffer internally. Now, we're using the internal array. I've called these static arrays a bunch of times. Really, it's just an embedded array. These bytes are now part of this structure. So, however big this thing is going to be, it just becomes part of this this thing here. That's why we don't need to allocate or dimension these things, or you can't undim them or grab the handles, because they're not an array that's dynamic. They're just a bit of memory that's added to here. This data is no different than these. Absolutely none. You know, I could just do the same thing here and just go, you know, for each pixel I could just go, you know, sorry, pixel 1, 2, 3, etc. for however many pixels I needed. What I am doing though is, since these are since this is an integer array, and internally we think of our little sprites as being a byte per pixel, so they're 32 by 32, which is the default the library sets to. So up here I'm computing the size. I'm going just width by height, that gives us the number of bytes. But because this is an integer, which is 4 bytes, I'm dividing that by 4. That gives us an appropriate buffer size. If I read the pixels out here as via an array, I would be reading 4 pixels at a time. Which you could do if you wanted to copy the sprite that way, but you can just do a duplicate, or copy that in memory. Since there's no strings in that, you can just go get a pointer to here, get the number of bytes of this thing here, and do a copy. And that would be the quickest way of doing it. That does mean that you're copying, if you copy the whole thing, you're copying the status, the depth, the position, everything. If you get the address of the pixels and just copy the pixels, that would just copy the frame, the image that you want to be displaying. If that makes any sense. But yeah, that's pretty much the guts of the library. So we've got our raster interrupt approximation, or a copper list approximation in there somewhere, which is what this is doing. The background, this has changed a bit since the other day. I was just messing around with it. So we've got a bunch of these. I've got 2 loops there. We're running through 360 degrees, and then we're using to compute the sinus of how much of the color we should have. That's how we're getting a band of each color. And then once we get to the end of that, we're just going to the next color in the raster bar table and doing it again. Just moving down the screen until we reach the height. One last time. So that's our backdrop. It's a bit dodgy, the routine itself. I mean, it's all thrown together. Yeah. If you want to do something like collisions between sprites, I'll probably add a little routine to do some detection of detect when the rectangles overlap, and then check the pixel buffers themselves. So you could actually do good old-fashioned, sort of hardware detections as you would have in old systems. But those systems tended to have, there was like a status bit. I'm not sure how it was implemented in every computer, but there was the machines would only do the comparison after the scan line has been rendered out to the monitor, because it doesn't know until then. Yeah. Anyway, bit of a weird oddity, isn't it? But yeah, it runs pretty well. I'm just using 165, whatever the latest build of 165 is. Nothing special. And if you looked inside the code, as we were just doing before, you would see that the routines themselves are nothing special to the code. That's doing the resolution copy. So we've got a separate routine for every alternate width. I did update this a little bit. So when we've got pixels that are meant to be 2 pixels wide, so we've got 1 byte in memory, we're going to copy those out to be 2 bytes in the output. So here what I've done is I've divided the width by 2, and then so I'm reading a pair of these things at once, grabbing the 2 pixels and then using the ARGB to combine the combination of the first pixel and second pixel into a double pixel out on the other end of that too, because really just ARGBs are just, they're packing 4 bytes into one 32-bit integer. Once we have that, we just poke it into memory. So we're doing half the amount of pokes and half the loops. And here's just the leftover. So if we have a width that's not a perfect, not divisible by 2, we might have pixels that are left over. So that's why you need those things there. Otherwise here I haven't bothered with. I think I did the size 8 as well, yeah. You might not know this, but there's a second or some other variants of poke int that do a bit like the fast.2, fast.3, fast.4, where you can do you can poke a pixel or write a pixel and then put a color next to it, and then with fast.4, for example, you're writing to the coordinate that you want to, and then 3 pixels beside that. So it turns one call, or it replaces what would normally be 4 function calls with 1 call, and you're only pulling for the buffer once. It's a lot easier for the function to do its work, because functions have a pretty high overhead. The vertical screen processing stuff is this, where we're running down the frame. We're calling the copper list emulator to work out what the current colors in the palette are going to be, and then drawing the strip, looping back and doing it again. So at the very end of this, we copy the old frame buffer back to where it was, and we restore the palette as well, because the palette technically in old systems, when you modify the palette under a raster interrupt or a copper on a 64 or an Amiga, then those changes are there to stay. The Amiga mainly, because 64s don't have a palette. So if you change the color of or color 1 to RGB, purple or whatever you wanted to, and then halfway down the screen you change it to blue, at the start of the next frame that color would still be blue. What this does here is it resets where it used to be. So that whatever you set the palette to originally is protected each frame. Otherwise you have to keep reloading the palette in every frame. Just a small user-friendly little thing, I mean, using the library is pretty simple. I would hope so anyway. You've got an open screen. We set up our width and height and resolution of the pixels. Pixels have max resolution by 8. I did notice a weird thing that happens before. If I set this to, was it? Yeah, we don't get any output, so it's not, for some reason it's not drawing the screen in that mode. Don't know. Some of these functions don't have clipping either, so they just assume that you're going to give it the right thing. The text is now way off screen, the sprites are way off screen, so our resolution's changed. Now of course you can use the internal PB mapping stuff to do, you can use PB's mapping to do basic sliding collision around stuff and actually make a real Mario game if you wanted to. Like it might be fun to have layers in there as well, like multiple screen layers. Like classic systems like the Amiga have dual playfields, and other systems like the the Sega and the SNES in particular, they have different modes for different layers. I don't know much about those now off the top of my head. I can't think what modes they do have. The Amiga has dual playfield modes, but you can actually use palettes to create the appearance of two different playfields. Anyway, so set up a screen, and this one here we're creating 20 junk sprites basically to look at the screen, and one for our ship. That's the function there, write sprite. So there's a write to character, a write to sprite, etc. They're basically a dot command that happens to write to a particular sprite into that particular buffer. You can do it yourself. Just grab the pointer to the sprite sets, compute where the sprite is in memory, and then just access the array if you wanted to. Anyways, look, just pick through. You don't really need those. The set color palette here is the only public sort of function for the copper. The XG copper is used in sync. Write palettes for reading and writing the palette, drawing a dot, reading a dot, strip function, box function, CLS, that should just be fill memory, to be honest. Filled circle, just drawing some strips, drawing the text, blending a character across if you give it the source location and destination locations. In other words, we're just doing a raw memory copy in that particular case. Probably should have something like that there. So you could do map tiles, split the map tiles from an external location and just have it do just copy the characters across as quickly as possible. I'm pretty sure you'd be able to do a decent little scrolling game in low resolution pretty comfortably. We pull the resolution right down. We might crash it though, actually. Oh no, we're fine. It has a pause when you press the mouse button. That's that. Let's do that. Alrighty, that's pretty much all we wanted to go over. I think we've gone over all the functions. Our sprites have a create, a delete, position. We can grab the sprite's position. Set the sprite's position. Its X position, its Y position. We can read those back. Get the width of the sprite, the height of the sprite, the depth of the sprite, and that's for writing your data into the sprite buffer directly. There probably should be a copy to sprite or something like that, or copy frame or something like that, to make it a little bit more intuitive for people, and that would just use copy memory internally. What are we up to there? That's the draw sprite functions, which we looked at before. It's the depth function we looked at before. It's the font reading and writing stuff. Initialize the font, drawing a line, write to screen. You can just give it a target location and a source address in modulo, and then copy that raw bytes from that location onto the screen with no color zero masking though. That's the one thing you lose by doing that. Because it's palette based, I mean, what you could do, I mean, visually you can do a whole bunch of weird effects with palette trickery. It's something you just can't do with RGB very well. Because you've got a byte per pixel, like if you had a pixel, an index of, you know, of one, and that color, that index is in the palette. You know, if you've got here, and this palette here would be RGB white, right? With an RGB screen, you would add these raw RGBs together to do alpha addition or subtraction or to multiply them, whatever you wanted to do to do an effect or blend between the two ones. With palette mapping, you can't really do those things. But what you could have though was like a table. Let's say you had your index, and you think, well, we'll have a collection of colors in here, and then we'll have 10 levels of this or something like that. If I wanted to draw over the screen and change the indexes from index 1 to 2 to 3 to 4, let's just say there's four of them. Let's pretend they're all different. Yeah, pretty terrible example. I would have to go, conceptually, I'm reading the screen from an X coordinate and a Y coordinate. If I wanted to add 1 to that pixel, you'd be this going, equals this plus 1. But if I need that to be within a certain range or a particular, let's say I don't want this pixel I don't want this to do anything if it's already if the color is not one. If this pixel is equal to 1 and this pixel is lower than 5, then we do the addition and we write the output back into the frame buffer at the same location. So if we draw a dot, if we process the screen like this, then any pixel that was in was color index 1 would be bumped to color index 2. So on screen it would look like it's changing. That RGB's changed, but that would change for that pixel, right? When we did it again, 2 would become 3, 3 would become 4, and then it would stop, right? The trouble is with that though is you've got lots of logic for each pixel. So if we had a frame buffer that's, if we're doing, flesh that out a little bit, we're doing from here to width, sorry. Same with height, doing that for height, bump that in a little bit so you can see what's going on. Now, if that frame buffer is, I don't know, 100 by 100 pixels, we've got 10,000 pixels, we're doing this logic 10,000 times. What if we have a bunch of these different things we want to do to pixels if they're a particular index on this frame? What you could do is you could have an array, like a pre-computed table, remap table, I guess. Now we only need 255 of these because they're only 0 to 255. What you would do is you run through, compute all of the possible responses. And you'd apply your logic in here. So not reading from the screen, we're reading from this, just go loop, doing the same logic, and this would just be this pixel. So if this pixel happens to be between 1, 2, 3, and 4, we're going to add 1 to it and move it. Every other pixel is not going to be changed type. So the inner loop then just becomes this. You don't need this logic. Right, all we need to do is remap it through here. Now we've got a fixed cost for the frame, but we can have 10 different calculations being done within inside this thing here, and that cost per frame is the same. It makes no difference to us. So you could do effects like that. Yeah, just saying. I don't know, just trying to put some ideas out there, trying to make people think a bit laterally. Look, it's a weird thing to do. I've seen a bunch of these sort of little demos around lately that do this low resolution stuff. Just thought it might be interesting, might be a bit of fun for people. It's not going to set the world on fire, that's for damn sure. But it's just how we roll here at PlayBASIC. Let's reset that back to where we were, which was 256. 256, 2 by 2, thanks. Yeah, back to where we were. Hello. If you had a map created in PB's mapping commands, you can't render that to this screen, but you can use that for collision purposes. So what I was trying to hint at before, you have your sprites running around the frame, and then copy the blocks you want to copy onto the back buffer, and then you're golden. That's all you need to do. Just change the palette map. I mean, classic systems have hardware scrolling. I did think about adding that actually, but I can't think of a way of emulating it with how I've added sprites. We need multiple parsers. Should load some proper sprites, I guess. Would make it more interesting for people, but it's a fun tech demo thing. I mean, who cares, man? Alrighty, that's enough of that. Thanks for watching, and I'll see you next time. I'll just chuck this up in the forums as usual, and you're welcome to play with it and do whatever you want. I don't care. Alright, see ya. Bye.